Hello and welcome to more Cosmology. I'm Jason Kendall and I've been going through Dr. Barbara Ryden's textbook, Introduction to Cosmology. This is Chapter 3, Section 4, Describing Curvature. Today we're going to answer this question. What exactly is spacetime curvature and how can we describe it? Before I begin, I just want to say thank you to my Patreon supporters as well as my YouTube members. Their support means a lot to me because it does keep this channel going. If you like what's been happening on the channel so far, please join up. I also give all my supporters and members special perks and advanced views. So let's begin. What exactly is spacetime curvature? Last time we looked at how the Einstein equivalence principle shows that an accelerated reference frame can be the same as a uniform gravitational field. This means there is no experiment that can tell the difference between a uniform gravitational field and a uniformly accelerating reference frame, such as a rocket going up in space, whatever upward means in space. Also, when you drop a couple of apples here or there, their descent would be the same as if you dropped them on Earth. If you threw them to the right, their descent in both reference frames would make a parabolic curve. Now that's for the trajectory of falling objects. We also find that the equivalence principle dictates that light's path must also bend in a gravitational field. We found this by looking at the behavior of a laser in an accelerating rocket and applying the principle to show that it'd be the same on Earth. We're always assuming in these examples that the rocket's acceleration is the same as the Earth's, that is, 9.8 meters per second squared. This is one of Einstein's great predictions, and it was borne out in the solar eclipse of 1919, where Eddington went and found the actual deflection of starlight as a result of the sun's gravitational field. Another test of relativity that shows this strangeness of gravity is the gravitational redshift. Inside of a uniform gravitational field, the light that is rising up and out of a gravitational field will lose energy as it traverses that distance. This was first quantified and tested in the Pound-Rebka-Snyder experiment. This experimentally demonstrated there is a loss of energy by photons going up inside a gravitational field. All these things kind of give us a hint that space and time are a little bit different than we expect them to be. In fact, they're significantly different than we expect them to be. So let's ask the question, what exactly is space? Because when we talk about space-time curvature, we naturally come up against a lot of preconceived notions, as well as that age-old bugaboo common sense and how it makes us want to think or not think about the nature of space and time. In this lecture, we'll focus exclusively on spatial curvature. I get a lot of questions in my videos' comments where people ask and plead and demand to know what space-time curvature is, and specifically, what's it curving into? It is very sticky for a lot of people to get the hang of the idea of what we mean by space-time curvature without it actually curving into anything. This is the key concept I'll try to explore today. Because general relativity and all of physics are mathematically based, and the language of physics and the language of cosmology and the language of astronomy and the language of science is mathematics, we must allow the logic of mathematics and its proofs and theorems to guide us in our search. The gold standard is when a theorem or proof gives us a method to test it in the real world. Theoretical physics is all about creating testable predictions based on other tests through mathematical analysis. We'll walk that walk and see where we end up. So let's start with the mathematical concept of space, which starts with just a bunch of points. That's the first concept of the idea of space, simple labels on points. Notice I did not say location in space. We'll first start by defining a space as a set of points. Next, how you relate those points together is really important. This is the topology on top of all these points. This topology will define the relationship or relationships between and among all the points. Perhaps it's just a map of this one, then that one, or these are alike and those aren't. Basically, we'll need to define how you get from one point to another as a way of thinking, or if there's any relationship between the points. And that's what we mean by space. It is not just some set of points, but it's also their interrelationship. And now we see our first bias and prejudice. We will likely ask, what's the distance between a couple of points? But that question is not a needed one for the relationship among the points in the space. They may be completely discrete and separate, so there may be no thing between some subset of the points or even all of them. Our points may just be labels for objects, and as mere labels, they don't contain a distance-like quality. At this point, you may be thinking, yeah, but that's not what we mean. I agree. It's now important to note that all of physics relies on a concept called a metric space. This means you have some rule that allows you to make a measurement of the distance between any 2 points in a space. And we're not going to say in space. I'm going to keep saying in a space. This important distinction arises because of our concept of space as a set of points. This is where common sense starts to fail, because the very way you measure a space is a matter of experiment itself, and not in the construction of rulers and levels and protractors, but in the way the tick marks of these instruments rely on a groundwork of assumptions about your world. Staying with the idea of a metric space, we can safely eliminate a huge swath of different kinds of spaces. A metric space is a space that allows you to make a distance between points. Now, we also have to have another set of concepts about space as well. We also wish to stick with some parts of our intuitive notion of space. Our intuitive notions about space contain the concepts of homogeneity and isotropy. Homogeneity means that pretty much if you look in large enough scales, everything is roughly the same no matter where you stand. It's much like the idea that all cities have a Starbucks on every corner, serving the same coffee, or that every medium-sized town has strip malls and McDonald's. It is this concept of homogeneity I'm after. Now, there may be small differences when you look closely, like there may be some bookstores that sell comics in one town but not another. Or there may be 2 independent coffee shops in one town, but none in another. But over large enough samples of towns, these differences smooth out. Or more specifically, looking at the county level, containing many towns, you start to see the same contents. No matter where you go, it's about the same stuff. A sad thought for some, but let's leave that alone. It's a core assumption in cosmology that the universe is filled with the same stuff, which behaves the same way on average no matter where you are. That's the concept of homogeneity. On the left-hand image, we see throughout that sphere pretty much any place you would go inside that sphere has some upward-directed arrow. Also, every location has roughly the same number of arrows in a given volume, and they're all pointing in the same direction. So that is quite homogeneous, but it's not isotropic because there's definitely a preferred direction of orientation. All the arrows point up. Isotropy means that it looks the same in every direction. Now, in the right-hand side image, it's distinctly isotropic, but not homogeneous. We can see there are different densities or different hashes. The stuff that's close to the center is clearly different than the stuff just beyond it, and then there's a sphere around that that's again different stuff. So it's isotropic around that one central point. And if we were there, looking around us, we'd see those 3 different layers all layered the same in every direction. But if we take a step to the edge of one of those spheres and look in every direction, now it's not isotropic. There would be different layers in different directions at different distances. That's the isotropic concept. But homogeneous, it certainly is not. Because if you take a bucket in any one of these areas, you're likely to get different stuff. So these concepts of homogeneity and isotropy are kind of the way we think about space in general, and this is experimentally verified. It doesn't matter what direction you look, it's roughly the same in all directions. And it doesn't matter where you are in the universe, you'll see roughly the same stuff around you and in equal parts. Both homogeneity and isotropy are part of what we call the cosmological principle. But it's also kind of intuitive in a way, and it helps us. Another thing that it helps us with is the nature of our coordinate systems. Now this is where we're starting to talk about what we really mean by the nature of space. Here's a metric space, meaning that each point in the space not only has a label x, y, z, or r, theta, phi, but also has some rule to measure the distance between the points. The labels make it clear that we're working in a 3-dimensional space. This means to fully and exclusively parameterize every point in space, we only need 3 numbers. These numbers can be assigned to places on a grid. Now, the grid of coordinates is not unique. There is an infinite number of possibilities, but we will stick to orthonormal coordinate systems, even though that is not strictly necessary. By contrast, a non-metric space would not necessarily even have enumerated locations on some grid. It just might have some index or some non-numeric naming convention for each point in the space. Luckily, we won't need to learn any more about such spaces. It is the application of some parameterized coordinate system to the space that solidifies the concept of a metric space. Let's declare that one step equals 1 meter. We can also declare that we can make a curve that smoothly traverses between two locations, and that each point on that curve can be associated with some real number, not just integers. Measuring the length of that curve, whether it's a straight line or some bendy, loopy path, is facilitated by the thing called the metric. The metric transforms points in a space, each labeled with coordinates, into a distance between the endpoints of the curve. Again, the curve between 2 points can be called a path, and this path curve in a metric space has a parameter that, as we go from point to point, will translate the continuous smooth set of points on the curve into a distance. Of course, the most common system for labeling points in a space, is the Cartesian coordinate system, with orthogonal x, y, and z. We can also use a different kind of orthogonal coordinate system, the spherical coordinate system. Here we have a radial coordinate, which is some distance away from the arbitrary origin or 0 point. Next is theta, which is an angle from the z-axis down to the radial coordinate. Finally, we have the phi coordinate, which is just like a longitude rotating around the xy plane. Now notice that the center or 0 point or origin of the xyz system is arbitrary. That's a concept of a homogeneous space. We can set up our origin anywhere. As for isotropy, the exact direction of the z-axis is arbitrary. We'll call it up. But what exactly is up far away from a gravitational field? Thus, our orientation is also arbitrary, so therefore it's isotropic. It's easy to show that we can transform the Cartesian xyz into r theta phi. The dl of both these metrics is the distance between any 2 points in this metric space, and they are exactly the same distance. They only differ in their coordinate labels. Here we're only showing 1 point. But if we had 2 points, then their distance will be some distance change in x, some distance change in y, and some distance change in z. And that will give us the total distance change, which gives us a length between the 2 points. Importantly, a space doesn't care about what label it is. We use the most convenient label to solve whatever problem we have. Neither one is the one correct coordinate system. Also, the labels themselves, therefore, are arbitrary so long as they span the dimensionality of the space in question. The metric itself is also, in a very real way, independent of the coordinates. Its job is to translate coordinate differences into a distance. Let's now look at the difference between polar and spherical coordinates. Polar coordinates are just a different way to map points on a 2D surface. I won't use the word plane because that has a specific meaning, as detailed by Mr. Euclid way back in the day. Spherical coordinates are in 3 dimensions and cover a 3 surface. That's an ugly way of trying not to use the word space. In both cases, the choice of origin is arbitrary, and though the coordinate setup looks different in each, the 2 different pairs of coordinates, the xy in polar and the xyz in spherical, in each case, the surface or volume is fully spanned and labeled by the 2 coordinates or 3, depending on the space's dimension. The 2D case does not necessarily need or rely on any aspect of a 3rd dimension, and by extension, the 3D case does not need or rely on a 4th spatial dimension. In addition to spherical coordinates, we could use cylindrical coordinates. Basically, they're just polar planar coordinates with the z-axis sticking orthogonally up from the plane. So we have this very simply connected space and spaces. And these coordinate labeling things are giving you an implicit bias about how you think about space. We think, well, once you're out in space, there are no restrictions on your movements. And why not? I mean, there shouldn't be any unless you run into an asteroid or something, and unless you're writing some good sci-fi, you don't think of, say, going into space and all of a sudden hitting some wormhole or hitting some block in space or a boundary in space where you have to go around the boundary or you just can't go past a boundary in space. We don't think of space like that. We think of space as going on forever, just like Euclid said. And all these coordinate systems that we've been looking at support this common sense idea about space. Unfortunately for our common sense, there are an infinite number of spaces that are homogeneous and isotropic, and only exactly one of them abides by Euclid's axioms. To show what I mean, let's take this concept of a cylindrical coordinate system and play with it for a little bit. My goal now is to dislodge some of the biases you may have concerning the, quote, obvious nature of space. I'm going to help you first with the old 1979 video game Atari Asteroids. When you play Asteroids, you're piloting this little spaceship around trying to blow up some asteroids, and as you do so, the asteroids float through the space of the video game. Now, if a rock or an asteroid goes off the right-hand side of the screen, here denoted by the green boundary, then it'll appear immediately on the left-hand side on the other green boundary. Therefore, the right-hand side and the left-hand side are stitched together, kind of like a cylinder. It's very similar to the coordinate system we just looked at, except now you can't go into or out of the screen. You are in a two-dimensional space that feels like it has three dimensions. A good way to describe it is by imagining that the left and right sides are stitched together into a cylinder that has some fixed radius. And this radius is easy to describe. Take the width of the screen and divide it by 2 pi. That's the radius of this cylinder. Now, this is still a completely 2D space. It's just not a simple space. The relationship between the points in the space is different than the simple Euclidean plane. However, a cylindrical surface can still abide by Euclid's axioms. We next throw Euclid completely out in the asteroids game because the cylindrical space is also reflected on the top and bottom. It's a double cylinder. The top is stitched to the bottom in exactly the same way the right and left-hand sides are stitched together. So you can go up, cross the top, and then appear at the bottom. Now that's very hard to visualize. In addition, it's not a sphere. A sphere would also stitch the right-hand side and left-hand sides together, but the top line would now need to become a point. Also, spheres don't connect the North Pole to the South Pole. This means the space of asteroids is a torus or donut shape. To see why it's a torus, imagine a circle drawn on the screen. As long as the circle doesn't cross the stitches, then you can shrink the circle to a point. But if the circle is big enough to cross the stitches, then the best you can do is to make it a straight line. But notice we can still describe the entire space of asteroids in 2 dimensions. We just have 2 special rules that we add to it. Go off the right, come from the left, go off the top, come up from the bottom. But the location of those stitches is arbitrary. It's just the boundaries of the video screen, and that's all it is. The visualization of the torus that you see exists only to help you understand it. Philosophically and mathematically, there is no physical reason for the 3D world to exist in which the torus appears. We only need the 2 dimensions on the surface of the torus to make the Atari game space work. We can further demonstrate the potential weirdnesses of spaces with some etchings by M.C. Escher. His Ascending and Descending from 1960 displays 2 lines of monks, one continually ascending and the other continually descending on the same set of stairs. The stairwell is drawn to be a perpetual loop. An interesting concept because this is a 2-dimensional surface, right? A piece of paper. And on it, we have a 3-dimensional sort of building, which obviously cannot live in a normal 3-dimensional world. No matter how you would look at this building, it can't be built in reality. One of his classics is Relativity from 1953. This one is even more mixed up than the Stairs of Monks. You can't imagine or determine which way is down because there are so many downs in this image. You can continuously traverse this stairway around and around and around, or down and down and down. And each time you do, you have to rotate your orientation based upon the current notion of down. So this is a non-simply connected 3-dimensional sort of space that is projected onto 2 dimensions. But to its embedded dimensionality, there could be perhaps a 4th spatial dimension. But I'm not sure. No matter what, this can't exist inside of any 3-dimensional real universe. Importantly, though, how would you assign coordinates to this space? No matter how you do it, you will necessarily need to have cross products in the metric. That would mean that the distances would rely not just on the squares of x, y, and z, but on the products xy, yz, and xz. What a yucky setup. I leave its devising to an extremely intrepid student. The real reason to talk about all this is to loosen up the concept of space and dimensionality. We can clearly create, quote, impossible objects so long as the objects obey certain rules. Then they no longer appear impossible. We can create rules of spaces that allow for non-simple connectivity, and non-trivial spaces where lower dimensional spaces can be sufficient in of themselves without demanding additional, hidden, or imperceptible dimensions. This is the beginning of the intuition to understand why space can be called curved, yet it doesn't bend into anything or out of anything. We won't deal with spaces like Escher envisioned. We will look at spaces that evidence seems to point to that fit our reality. Remember that a space is simply a collection of points. We can relate sets of these points to other subsets of these points in any way we choose. But it's a matter of experiment as to whether or not these connections we chose fit reality. Our intuition may not be the correct guide. For example, we know from previous lectures that the path of light is curved in a gravitational field. Now let's see what we get when we look at the universe's global curvature. We have to start by going a very long time ago, 300 BC, to visit Euclid. He wrote the great masterwork on geometry called The Elements, which is very much worthy of study today. Every high school student doing geometry studies Euclid's axioms. These 5 axioms of Euclid are fundamental and give us the basis of what we would call flat space or uncurved space. This starting point harkens to our most intuitive way of thinking about space. The first axiom states that you can draw a straight line segment joining 2 points. It may seem obvious, but that's the purpose of axioms, to explicitly declare our intentions. What an interesting concept, because you can take any 2 points, no matter where they are in space, in a Euclidean flat space. Now let me start using that word, a Euclidean flat metric space. We can now draw what we might call a straight line between them. We don't have to curve around anything to join these 2 points. The fact that Euclid uses the word can here is also interesting. It implicitly means that along that segment, we can stop anywhere and choose any of the infinite number of points on that segment to make a shorter segment. The second axiom extends the first to state that carrying the line's direction along the same direction it was a tiny step ago, we can make arbitrarily long segments, each dense with points. This is a key concept of the real number line and a key idea of what we think of as space. We can always find space between any 2 points. Furthermore, the space between them has no kinks, whereby we have to change direction in order to go from one point to an arbitrarily close point. This changes and extends the idea of a line segment into a line. In relativity, we would call this concept a geodesic. Euclid's second axiom posits an infinite universe. He means that every line segment points off to infinity in either direction of the segment. You just have to take the time to walk it, which of course you can. Again, I want to point out that you could lie an arrow down on the segment and push it along so that the arrow is never askew from the segment. The arrow will then stay pointing in the same direction as you push it off to infinity. The third axiom now relates line segments to areas, and specifically gives a method to create the model of perfection, the circle. The third axiom could have used a square to give the concept of area, but the circle was a deep puzzle to the ancient Greeks. They understood that even though it could be created with a fixed length segment, there is no integer or fractional value of the segment that can be laid perfectly around the circumference. That's the whole 2 pi r thing. It was quite a mystical concept, but this was just a small part of why circles became regarded as symbolic of the celestial or heavenly realm. Euclid was giving us a way to relate the mundane to the sublime. The fourth axiom is also very odd on the surface. Axioms are weird because they always state the obvious. So, right angles are congruent. This simply means that every right angle is the same as every other right angle. That's an interesting statement of the homogeneity and isotropy of Euclidean space. Euclid here expands his geometry into the third spatial dimension by taking the highly obvious exercise of taking a t-square and rotating it around in your hand in any possible orientation. If you take a t-square and rotate it, Euclid's axiom states that it does not change. It also states that any reader of his elements can do this at any location, and implicitly at any time. Only the second axiom asks us to try to do some action by extending a line segment. This second axiom states that if you were to do this, then there is no end to the line or its straightness. The fourth axiom allows us to toss right angles around however we want at any time in the past or future, and they will always stay the same. We can also note that a right angle is composed of two line segments. This axiom also means that we can extend the segments indefinitely, and that angle stays a right angle. We can take a segment out of the infinitely long lines radiating away from this right angle vertex and drag it, arrow style, all the way back to the right angle vertex, and it'll still be lined up with the original line segment of the right angle. This is a really important concept to grasp as we go forward into curved spacetime. Euclid's line segments, once laid down and extended, keep their orientation and their straightness in the common sense way of thinking, and in the carried arrow way of thinking. Spacetime curvature will have something to say about this. Now then, the fifth postulate is the one that we're going to play around with a lot. Let's start with two lines. These are our infinitely extended lines. They could be in any orientation in 3 dimensions, but we want them to be in the same plane. So now we have these two lines. Now we toss a third line into the mix such that it intersects both of our original lines. If we examine the interior angles of both sides of the intersection, we will then choose the side where the sum of the two angles is less than the sum of two right angles, that is 180 degrees or pi radians. Let's then follow our original two lines on that side all the way out to infinity. Euclid's axiom says that well before we reach the lazy 8, those two lines must intersect. Now this is an interesting thought. It's distinctly not like a pair of train tracks. Train tracks, even though they do seem to converge in the distance, we know they never do. The railroad ties keep the tracks at a fixed width for the length of the train track. This means that at every point along the train track, the ties intersect at 90 degrees or at right angles to the tracks. The train tracks are parallel, but generally, two lines extending off into the distance are not. For any two lines on a plane, there's exactly one orientation of both lines such that they are parallel. All other orientations mean that they will eventually intersect. This is the concept of Euclid's fifth postulate, known as the parallel postulate. But here's the thing about the parallel postulate. It was found in the 19th century to be unprovable from the other four postulates. It was also shown back then that we can devise mathematical spaces where the fifth postulate does not hold. That is, where infinitely long straight lines in the loose sense pointed towards each other away down the road will never intersect, even if they're on the same plane. Likewise, we can devise spaces where such non-parallel lines intersect an infinite number of times. Worse, we can make spaces where in one place, say where you started, they're parallel in the Euclidean axiom 5 sense, but far down the road they intersect, or diverge. There are an infinite number of spaces where the carried arrow idea gets messed around with, and the arrows get turned around, even though they were locally stepped along in the normal sense of the word straight. Let's start by taking a closer look at Euclid's second axiom. Any straight line segment can be extended indefinitely in a straight line. The sense is that we have some direction to that line and we want to take little steps in that same direction. So we can have an arrow that leads us down the line. This arrow is being moved with a process that we'll call parallel transport. Parallel transport really means moving a vector along a geodesic tangent to the space such that it remains pointing in the same direction as you move it in tiny incremental steps. For a flat space, this is a nearly trivial and obvious exercise. We can also parallel transport an arrow along a different geodesic that intersects the original geodesic. In both cases, we always mean to say that a geodesic is a straight line in that space. Again, in a flat space, this always means the trivially considered straight line. Notice in the second case that the arrow was parallel transported along the second segment but maintained its orientation. That's the essence of parallel transport. We can then define the curvature of a space to be the amount of deviation, if any, that a parallel transported arrow endures as it is transported around a closed loop. In a flat space, the arrow will always stay pointed in the same direction, never leaving its orientation. This is exactly the same as pushing the arrow around on a table and always keeping it pointed in the same direction. But in a curved space, the orientation of the arrow will change upon traversing a closed loop. The direction and amount of rotation determines the shape of the curved space at that point in the space. Here we still haven't limited spaces to anything. A space could be flat here, radically curved there, and only mildly curved somewhere else. But a curved space will always change the orientation of an arrow as it is parallel transported around a loop. So let's take a good first example of such a space. The surface of a sphere is a two-dimensional space. At every point on the sphere, there are an infinite number of tangent arrows that are in the space. Let's choose one such arrow and take it to be pointing towards smaller longitude. Now let's step that arrow along a geodesic, here the equator of the sphere, always keeping the orientation of the arrow as close to parallel as you can as you step it. Now you might be saying, a sphere has a curved surface, so if you move the arrow at all, it'll have to rotate. And that's exactly true. So we have to move the arrow in such small steps that we cannot sense this change. However, even if we do this, the changes will add up. We turn the arrow now to go longitude line up to the North Pole. This is a bit easier to get since the curvature isn't in the direction of the arrow. Once we get to the North Pole, we descend back down the longitude line leading to our original starting place. When we arrive back home, the arrow has been rotated. Each step of the way, we took pains to assure that the arrow was always carried parallel transport style along the geodesic in a straight line on the surface of the sphere and remaining pointing in the same direction. Obviously, the surface of a sphere is curved. It's always interesting to do parallel transport for the flight path of a plane. Taking this very long flight from LAX to Heathrow is done on the geodesic, Great Circle line in red, and certainly not the black line. However, just for fun, take a black arrow and point it in the Mercator projection from LAX to Heathrow. The angle between the Mercator straight line and the true Great Circle straight line is 49 degrees. Notice how the black arrow, when transported between 2 points on a straight line in the two-dimensional spherically curved space, will rotate quite a bit. The black arrow is basically the viewpoint of someone looking out a window, and the pink arrow is the true direction of the plane. If we were to have instead forced the transport to occur along the blue line, which appears straight, but is actually the curved line, the same rotation would occur. And this is because instead of one big path as we see here, there would be ever tinier small hops from point to point. Each smaller hop would be closer and closer to a Euclidean straight line. However, because the Earth's surface is curved, these little hops along the truly shortest distances will still add up to the same total rotation as before. Let's now examine the three uniform, isotropic, and homogeneous spaces. All three have globally uniform curvature. This means that every point in the space experiences the same exact curvature. There is no mix of flat and positive and negative curvatures in each of these. Again, the curvature is always best noted by its impact on navigating the perimeter of an area. To help show the effect of curvature, I'm going to see the effect of an arrow that's tangent to the circumference of the circle in the space. This is different than parallel transport. In a zero curvature space, the circumference of a circle is equal to 2 pi times the radius of the circle. In this case, this also means that the tracing of an arrow tangent to the circle works out to be the same as parallel transporting the arrow around the circle. A flat space circle has circumference of the expected 2 pi d, where d is now the radius, and now 2 pi is the total angular rotation of our tangent arrow that it will incur as it traverses the circle. As we saw in the positively curved space, the arrow will lose some of its rotation as it's transported around a closed path. The lost angular shift is due to the circle's circumference being shorter than that of a circle with the same radius in a flat space. We saw previously in a counterclockwise traversal that the arrow's rotation loses some angle in a counterclockwise sense. From this diagram, it's like a chunk of the space is missing compared to flat space. If we follow the red arrow around the circle starting from the bottom, we see that it doesn't fully rotate compared to the flat space circle. However, it still did execute a circular path in the two-dimensional positively curved space. The area of such a circle is larger than a flat space circle, but its circumference is smaller. This should be familiar to you when you look at global maps of the Earth. Any projection distorts the sizes of the continents. A sphere must be spread out in order to be projected onto a flat surface. To retain the sphere's spatial proportions on a flat surface, you have to slice it into ribbons as we see here. The diagram shows us traversing a circle that's a latitude line, which is not a great circle. This means that when you parallel transport it, the arrow has to change orientation as it hops from one great circle to the next in tiny, tiny steps. In my red arrow example, it has not been fully rotated by 360 degrees or 2 pi radians. It's short some tens of degrees. In the negatively curved space, this transport of a tangent arrow around a circle would result in completing the entire rotation and then some. This is because the circle circumference, in this case, is greater than the flat space case. The parallel transport would pick up that greater length as the arrow hops from one tangent in the space to another. Rather than great circles in a negative space, we could call them great hyperbole of the space. In short, it's encountering a greater angular change as it's carried along the circle. These circles' areas are smaller than flat space circles, but their circumferences are much, much larger. Again, curvature is defined to be the change in rotation of a tangent arrow in the space as it traverses a closed loop. Let's look at each of these spaces in turn in greater detail. Let's start by looking at two-dimensional spaces. And we'll also exclusively look at homogeneous and isotropic spaces. That's very important. Having two dimensions in a space means that there are two and only two free parameters for assigning locations to events in the space. Two-dimensional spaces can be called surfaces if they are embedded in a three-dimensional space. We'll learn more about embedding shortly and why it matters or it doesn't matter. In Euclid's flat 2D space, we can use the simple metric that we see. It is sum total dl squared, which equals dx squared plus dy squared. In more detail, we've got an x-coordinate, which is left and right, and y, which is back and forth. A little change in x is called dx, and a little change in y is called dy. You square and add them to obtain the square of the distance between 2 points, x1, y1, and x2, y2. This extremely simple relationship transforms the coordinate changes between two locations into a distance. The metric can also be expressed in polar coordinates rather than Cartesian coordinates. We declare x to be r cosine theta and y to be r sine theta. The r is some radial distance from some declared origin point. Theta is the angle from the x-axis towards the y-axis that this radial distance points. These two metrics, though they look different, will give the same answer to the question of how far apart any 2 points are on a flat 2D surface. And this is our first metric. It is, admittedly, a very basic metric on a flat two-dimensional Euclidean surface. But don't worry, things will get more complicated. Notice right off the bat that this metric in both coordinate forms is inherently isotropic and homogeneous. The origin point is arbitrary, and there's nothing in the metric that says anything special about the locations or orientations. There is no cross product of dx and dy, and there are no rules say that if you go over here, you'll appear over there, like in asteroids. A key idea about a flat space involves the interior angles of polygons, and so let's start with a triangle. If you look at the interior angles of triangles, let's call them alpha, beta, and gamma. If we add up the total number of degrees of the three angles inside that triangle, we get 180 degrees, or pi radians. It wouldn't matter which of the metrics you use to derive this angle, you'd get the same result. Everything that Euclid would be comfortable with is on this slide. And let's see where that comfort breaks down. Now let's look at the surface of a sphere. A spherical surface is still a two-dimensional surface, and it is distinctly not flat. It is certainly curved. We can call that curvature positive. Why? Because the sum of the interior angles of a triangle and the surface of a sphere is always greater than 180 degrees, or pi radians. The angular size difference is the area of the triangle divided by the square of the surface's radius. So now I need to start to talk about embedding. Embedding is for visualization purposes only and does not reflect another degree of freedom. The radius of curvature is not an extra dimension in space. Rather, it is a characteristic of the space. We can get the sense of the embedding here by noting that the little r is the distance on the surface of the sphere from the North Pole down to some point. That means there's a maximum distance between any 2 points, pi big R. This is one time where the choice of coordinates is a big help. Note that in the Cartesian coordinates, we would have to have x, y, and z, but with the restriction that the sum of the squares of these three coordinates is some fixed number r squared. The addition of this restriction on the Cartesian coordinates reduces it from a 3D space down to a 2D space. This metric with this restriction is certainly valid, but it's clunky and it's messy to use. You sure could eliminate the z-coordinate, but it's pretty repulsive. It's better to simply use a better coordinate system that fits the space. This is the plane polar coordinate system adapted to the surface of a sphere. Little r is the distance down from the North Pole, and phi is the longitudinal angle. The large type metric looks very different than our flat Euclidean space. Note that there are only 2 degrees of freedom, little r and phi. The big R is the characteristic of the space of the metric and does not represent an actual positional option in a two-dimensional space. This all means that the spherical nature of the space, as we visualize it as a ball in the air, is not how the space is parameterized. The location of this ball in the embedding space is irrelevant to the discovery of the distances on the ball's surface. The actual size of the ball isn't really important either, except to create a scale factor if we want to measure in meters or miles or light years. No matter the size of the ball, we can devise 2 coordinates that are independent of the size of the ball to measure the coordinate distances on the ball. These coordinate distances will then be imbued with a physical distance when we determine the size scale of the ball using big R. In that sense, we can call this 2D space a spherical surface because this space shares many similarities to the thing that we call a ball. But as we can see from the metric, we are only ever making changes to little r and phi to determine a distance. Therefore, the embedding of a ball in the air is all just a mathematical trick to help you understand the space better. It does not imply anything about the space in which it is embedded. It doesn't even imply that such an embedding space even exists. The game Asteroids had a rule: go off to the right, come back on the left, that comprised the very nature of the space of the game. The developers did not need to solve any distances on toruses to find the curvature or the size of the space, nor did the game have to be viewed in the round. Nope, it was a flat screen with an odd rule. Here, we can look at the metric as just a mathematical tool for knowing the distance. The big R is just a scale factor, and the sine squared term is merely the only way to have a positively curved space that is homogeneous and isotropic. Many other functions could have gone there, tangent for instance, but only the sine function with that specific argument and that specific coefficient satisfies homogeneity and isotropy. Nicely, Euclid's parallel postulate fails for this space. All distance lines make great circles in this space, and therefore any lines that locally are parallel at some point will converge in both directions. Now let's derive the 2D metric that is congruent to being on the surface of a sphere. We start with a homogeneous and isotropic flat 3D Cartesian coordinate metric to define our embedding space. Next, I list out the x, y, and z coordinates in terms of their 3D spherical coordinates. I use r tick as the radius from the arbitrary origin in the 3D embedding space. Again, I want to emphasize that the 3D embedding space is a mathematical construct that should not be construed to actually exist. We know that the space we wish to bring into existence is only and exclusively two-dimensional. We're just using the concept of an embedded space to help us derive a 2D homogeneous and isotropic space as a subset of that space, which retains the properties. Let's get back to the coordinates. R tick is the radial distance from some arbitrary origin to any point in the 3 space. Theta is the angle at which the radial distance vector lies from the z-axis down towards the xy plane, maybe read it the equatorial plane. Finally, phi is like longitude. We'll at least keep that around for later. Our major restriction is on the fixed radius, which then allows us to make, say, the z-coordinate into a dependent variable. X and y remain independent. We now define a new r. This r is the length on the surface of the sphere from the North Pole down to the point in question. Theta was going to be an independent variable in the spherical coordinates, but now it's subservient to our new r. The greatest possible length of our new r is pi big R. Why not 2 pi r? Well, then we'd be going all the way up the other side, which could then be described with theta r, with that theta measured from the opposite direction. So big pi r is the largest length in this 2D space. With this restriction of our new definition of r, we have a new series of x, y, and z coordinates. These new values only depend on r, on little r, and phi. We can then take the differential and then square them. Adding up these squares gives the form of the metric we saw before. It's worth emphasizing that this new little r here is distinctly different from the little r of the normal 3D spherical coordinate system. It reflects the fact that we must measure the radial polar coordinate component of this 2D system in the system and not outside it or through it. We only measure distances inside the 2D surface. And when I say inside the surface, I do not mean the interior of the sphere. I mean we're only measuring the latitude and longitude positions on this sphere calibrated with the big R scale factor to know the distance. I use in because we do not care about the 3D embedding bulk that may or may not exist. Mathematically, we could have derived this without resorting to familiar geometrical ideas. It is a lot harder to do and would require some mathematics quite beyond the scope of this lecture, but it can be done. It is this embedding that trips people up and is the source of all preconceived notions that a curved space curves into some other space. The curved into space was a complete construct and helper function that merely gave us a shorter path to the same answer. Another way to look at it as the embedding idea is a model and not reality. The model is a good way to think about it, but like all models, it has its limits. If I'd never shown you the words spherical curvature and merely showed you the metric, you wouldn't have necessarily started with the concept of a 2D space embedded in a 3D space. You'd have just said, well, that's an interesting way to connect all the points in a 2D space, and left it at that. Unfortunately, for students of spacetime around the world, this bias lives on. The only way the 3D would come back is if some physical process happened to be on this 2D surface that demanded a third spatial dimension for its action. We are only and exclusively looking at length measurements, so the third dimension was there just as a helper tool and not a degree of freedom. For our third and final homogeneous and isotropic space, we have a uniform hyperbolic negatively curved space. In every location in this space, the space kind of folds away from itself. The parallel postulate here says that initially, parallel lines in this space all diverge, growing in distance apart. Concerning the sum of interior angles of a triangle, it's now less than 180 degrees or pi radians, where the difference is the area of the triangle divided by the square of the characteristic curvature. But what's this radius around? That's a good point, because when we look at a negatively curved space, we really cannot visualize it very easily. We see these saddle-type shapes as examples in books, but it's really deceptive. Why? Because every point in the space would be centered on a saddle-type shape, and all space around every point folds away from itself. And this is an infinite space, but its shape is radically different than the Euclidean infinite flat space. In some sense, the farther away you go, there's more space there. This can be seen in the odd metrics form. Compared to a positively curved space, the sine function is replaced with a sinc function, which is basically an exponential for large values of its argument. Unlike the uniform positive curvature, which has a maximum value of little r over big R, there is no maximum value for the hyperbolic sine function. Its role here is to make initially parallel lines diverge away from each other exponentially. The saddle shape is just a helpful visualization that the space is exponentially more dense than the flat plane. However, it's still only a two-dimensional space. We have to embed this in 4 spatial dimensions in order to get a 2-dimensional spatial metric. Those extra dimensions were, again, bound by restrictions that made them dependent variables to the 2 real dimensions. They then simply get tied up into the characteristic scale of this space, big R. This big R, again, is more like a fundamental constant of space and not a spatial degree of freedom. All right, so now I've summarized the three equations that you've just seen, and I've extended them into 3 dimensions. The symmetry of the angular rotation allows us to extend the metric from just theta and into phi as well. Theta was a longitudinal rotation, and phi now is an equivalently latitudinal rotational degree of freedom. It's the same set of coordinates we saw a bit ago when we examined the coordinate embedding of a spherical positively curved space in 3D. But without the radial restriction, we now work in all 3 dimensions. As we can see, we can simplify the equations by defining omega. In doing so, we can combine these equations into s sub k of little r to give us a happy shorthand notation. This function has 3 values depending on the value of k for the curvature, which can either be +1, 0, or -1, each one representing the curvature of the space. What's more interesting is that s of k of r can be represented analytically with that wild-looking function on the bottom right. These coordinates are called hyperspherical coordinates because they describe an embedding of a 3-dimensional space in a 4-dimensional space, as we derived previously. These equations represent what we might call a 3-surface of a 4-ball. That is to say, the 3-dimensional surface to a 4-dimensional hypersphere. Wild circumlocutions aside, the embedding is still just a mathematical trick or tool and not a reflection of a physically needed degree of freedom. With that, let's see what the form looks like when we embed a 3-surface into a 4-ball. Let's start with a space that has 4 spatial dimensions. We have our familiar x, y, and z, and now we'll toss in a mystical w. The Cartesian spatial length element is given at the top. A small change in distance, dl, is the sum of the squares of the little changes in each coordinate distance. Next, we'll add the needed restriction that we're looking at a 3-surface. Normally, we'd call that a sphere, but a solid sphere in 4 dimensions requires 4 coordinates. Thus, we're looking at what we would call a hypersurface. This restriction works out to be the sum of x, y, and z squared equal to our radial coordinate, little r. That's just the definition of our hyperradius. Our restriction comes into full force with the second part. W squared plus r squared equals big R squared. Now we've bounded the hypersurface with the big R. Big R here is the radius of the 4-ball that is wrapped by our 3-dimensional hypersurface. I've taken the liberty of converting x, y, and z into polar coordinates for the next line, and this should look quite familiar. It's the same thing we just looked at in the previous slide for s sub k of r for k equals 0. Basically, this statement means that we're embedding a curved 3 space in a flat 4 space. However, our embedding dimension is just a tool and not real. If we take the differential of our restriction condition and square it, we get dw squared equals dr squared times r over w squared. This leaves us with dw be converted into little r, scaled by the restriction constant big R. Plugging this dr back into the 4D spatial metric and sampling with a tiny bit of algebra gives us a new form of the metric. We can then define k to be the inverse of big R squared. Here, k is the curvature constant and can range from plus big values to 0 to minus big values. Previously, in the hyperspherical coordinates, it was either +1 or 0 or -1. This k is different. The final form of this metric for positive values of k is given on the right, where we've once again used the isotropy of space to emphasize the simple angular dependence. Not all 3D spaces can be embedded by placing them in just one more extra dimension. A 3-spatial dimension negatively curved space with k less than 0 requires 2 extra spatial dimensions for the embedding. I could follow the argument through here, but suffice it to say that the mathematics are tricky and the bang wouldn't be worth the buck for this video. As you can see, this simple restriction would lead us down into the complex plane, requiring a bunch of proofs about complex analysis and much more. The end result is quite similar, though, to the previous slide, except now that the values of k would be negative real numbers, and for your edification I've chosen to show the spatial metric for k equals -1. The saddle diagram here is a real failure for visualization. The cartoon only shows a poorly approximated 2D surface that is represented at exactly one point near the center of the saddle. Every other point in the space would also be represented with such a saddle shape around it, and such diagrams would get messy really fast. And that's just 2D surfaces. Now we're talking about a three-dimensional saddle. That would require being able to see it unfolding into that extra dimension on paper or screen, which is only 2D. The fifth spatial dimension is now required in order to accommodate the unfolding of the 3D hypersurface into an unfolding 4D negative space. It is this second step into a flat, five-dimensional manifold that finally gets us to our rotational symmetry. This is some ugly arcana. Perhaps one day I'll do a full video detailing this proof, but since it's not relevant to our current level of discussing cosmology, that is, we don't live in a space with 5 spatial dimensions, much less 4, I'll just stick with stating quite unsatisfactorily that it's serious maths that get us to this very simple metric we see at the bottom. The important thing here, though, is that we have a completely different form for the metric. The bottom metric is indicative of a globally uniform, isotropic, and homogeneous constant negative curvature three-dimensional space in some new coordinate system. Let's finally give a name to this new coordinate system. It's called the reduced circumference polar coordinate system. In this coordinate system, the little r is completely different. Importantly, the form of the metric in this coordinate system looks very different too. Here we have the curvature not being one of the three values, but rather some global constant with a real number value. The theta and the phi are the same as before. So what is this new r? Here is our metric expressed in two different coordinate systems. The top one is the hyperspherical coordinates, and the bottom one is the reduced circumference polar coordinates. The omega is the same in both cases. This is because of the inherent isotropy of these constant curvature spaces. In the hyperspherical coordinate system, little r is what you would normally think of as a radial coordinate. It's the distance from the origin to the point in question. In the reduced circumference polar coordinates, the little r is the length corresponding to the circumference of a circle centered on the origin divided by 2 pi. These two definitions of little r are not the same. They can't be used interchangeably, but the dl squared that they give rise to is exactly the same. There are very likely a whole lot of you are thinking one of the two questions at this point. 1, but isn't the circumference of a circle always 2 pi times the radius, so aren't these the same? And 2, why bother with making these two metrics at all? If you're going to get the same answer, why mess with these different ones? Can't you just tell me which metric is the right one? The first question is easy. We saw that in curved spaces, circles are either bigger or smaller than their flat space counterparts. The second question I can best answer by asking, what problem are you trying to solve? The first form will be helpful when we want to understand the angular sizes of distant galaxies, as well as keeping the form simple for the concept of distances. The second form is much more suited for calculating orbits. Each coordinate system has its benefits and drawbacks. In the textbook, Riemann uses the hyperspherical coordinates because we are frequently concerned with how the universe looks in all directions around us. We'll want to use this metric to show us how light rays traverse the cosmos from there to here. We show our cosmic bias because we're always at the center of all our observations. If somehow we could bop around the cosmos and construct a truly epically gargantuan circle or triangle out of lasers or cotton string, then yes, we would directly measure the curvature of the universe with the second metric. Irrelevant to its practicality, this would be an excellent way to measure the universe's curvature. But alas, we are tiny critters who will never make it to the next star in the next 100 years, much less into intergalactic space. We've been talking a lot about metrics and how they measure distances between 2 points separated by small intervals. I want to show you what a metric really looks like and how we get curvature from it. To finish out this long video, we have to lightly skate over some heavy maths. So buckle up, here we go. The metric encapsulates all aspects of the space into a compact form. It determines at every point P in the space the way we measure the distance at that point for each coordinate direction in the space. Thus, we have a bunch of coordinates, and they can be in any coordinate system that spans the space. The space has n dimensions, and we have some dxi or dxj for each one. The superscripts and subscripts I and j are just indices that help us keep track of the coordinates. With 3 spatial coordinates, we would like to use n equals 3, like we've been doing for this entire set of slides. The double summation sums over all possible combinations of the coordinates. I ranges from 1 to 3, and so j also ranges for our previous examples. We've just had the good fortune of choosing and working with metrics with a high degree of symmetry. This makes the components of the metric really simple. Here, in this particular metric, there are only 3 components. We could have had 9, owing to the double summation over I and j from 1 to 3 each, but we don't have any cross products of phi, theta, or little r. We only have their squares. As you can see, 6 of the 9 possible metric components are exactly 0. On the right-hand side of the summation, I've also reduced the form down to a simpler looking thing. I haven't changed anything significant, I've just used the Einstein summation convention. When doing such tensor algebra, if you have a subscript I that matches with a superscript I, then you sum over all possible values of I. Little g is the thing we call the metric. Let's say that when I equals 1, that coordinate is now assigned to little r. And when I equals 2, that's theta, and I equals 3, that's phi. This metric only has non-zero values for g11, g22, and g33, which correspond to grr, g theta theta, and g phi phi. Notice the values of g for each of its components vary from point to point, specifically for differing values of little r and theta. The coordinate value of phi doesn't determine the metric's values for any point in the space. This dl squared is just one example of a metric. We can imagine whole bunches of different metrics. Some may even have physical significance. You can write the metrics however you want, with any symmetries you wish, or with none at all. It's just important to note that the metrics encode all aspects of the space and relate tiny changes in the coordinates to physical length measurements. Let's see what we can do with a general form of g, the metric, and we have to remember that the Einstein summation convention is in effect. It makes our equations look a lot nicer, but we'll have to keep track of this one abstraction as we read along. In a previous lecture on the equivalence principle, I showed how light's path is bent in a gravitational field. I also showed that this path is called a geodesic. A geodesic is just following the shortest path in the space between 2 points. The metric for any space is given in the upper right. ds squared is now a space-time interval, and we're not restricting it to just spatial dimensions anymore. The gij is summed over the products of the various coordinates, which we're now allowing to have cross products. We can then define a thing called a Christoffel symbol, which is the capital gamma on the upper left. It has 3 indices, 1 upper and 2 lower. Each are different on the left, so no summing yet. But on the right, we see that it's the sum of the first derivatives of the metric, all times the metric itself on the left. Now, we have a mix of upper and lower indices, but importantly, the index L is the summed index. See how it's on top outside the parentheses, but on the bottom for the items inside the parentheses? That means we're summing things up according to the Einstein convention. So, while this is a shorthand for L ranging from, say, 0 to 3, we would have had 4 of these added together, one for each value of L. The summation convention keeps things compact and easier to read. But why does this thing exist, this gamma, this Christoffel symbol? What's its use? On the bottom is the geodesic equation. This equation shows how each coordinate, dxm, changes as you step a little distance, ds. The Christoffel symbol tells us the gradient of the space at a given point for each coordinate. As you traverse some small path length element, going on the shortest path, the gradient describes the path's curvature. Again, the metric contains all the facts about the space at each point, and the Christoffel symbol relates those facts to the shortest trajectory in that space, called the geodesic. The red line in the box is due to a gravitational field. That path is determined by the geodesic equation. The metric for that space is called the Schwarzschild metric and is applicable to stars and planets and black holes but not to cosmology. But that path is curved. So how do we then parameterize the curvature of the space, given that we can now determine the shortest paths in the space? Before we proceed, we need to see what these Christoffel symbols look like. Let's just go back to our original spatial metric with 3 dimensions. We have our original metric components in the red upper left-hand corner box. The components of the metric are only GRR, G theta theta, and G phi phi, each with the values that you see. To compute the Christoffel symbols, we also need to determine the upper index versions of the metric. I've put them all in the purple box. Each of these is the inverse of the double lower index counterpart. We simply want the product of the double upper with its corresponding double lower to be exactly 1. On the bottom are the things we need to calculate in order to get all the various Christoffel symbols. These are all the first derivatives of the metric with respect to each of the coordinates. Since there are 3 components to the metric and 3 coordinates, we need 9 first derivatives. I'm using the really compact comma notation for partial derivatives with respect to each coordinate rather than the more traditional dg dx style that you see in the Christoffel symbol. This makes it even more compact and for the ease of writing on blackboards and keynote slides. After doing the algebra, we end up with only 4 non-zero derivatives. Let's see how to use them. With these first derivatives of the metric in hand, I can now evaluate each Christoffel symbol, shown in green in the upper right. There are a whole wad of these because m, I, and j all have to take the various combinations of r, theta, and phi. Luckily, a bunch of them are 0. I'm only showing you the non-zero Christoffel symbols. The yellow ones all have the upper index as r. Here I've evaluated the upper index m for coordinate r. We get 3 non-zero symbols for r. Interestingly, each of them is dependent on the curvature constant k. For a flat space, k would be 0, which would simplify these symbols a bit. But k can be a positive or negative number that is constant of the space. It is in these symbols where the curvature shows up. The other symbols, which are principally angular dependency values, do not rely on the curvature constant. Also, none of the symbols depend on the coordinate value phi. These 2 factoids demonstrate the isotropy of the space. What they're saying is that if the gradient of the space as we orbit or curl around the origin at some fixed radius r changes due to the curvature, then the curvature in one direction would be different than the curvature in another direction. We already know that this is not the case, so these symbols just encode the isotropy in these mathematical artifacts. All these symbols can now be used to calculate the intrinsic curvature of the space. Let's see how to do that. The answer is here, the Riemann Curvature Tensor. A little while back I described the process of how we can determine curvature by parallel transporting an arrow around a short loop following geodesics. If the space is curved, then the arrow's final orientation and possibly its magnitude will deviate. Now we can finally quantify that statement. The Riemann Curvature Tensor is the thing you get when you actually do this experiment in curved space and make this measurement. This tensor, which you can think of as a powerful function, takes as inputs the coordinate basis for the space, some vector you want to push around the space, and the lengths of the sides of the loop. In this diagram, the starting vector is yellow v with an arrow over it. That's the red arrow pointing straight to the right above it. We then parallel transport yellow v upwards a distance dA. It might have changed a little bit. Then we parallel transported a distance dB to the left. This adds more changes. Then we parallel transported down a distance dA on the left. And finally, it's transported back to its original location through a distance dB to the right. The end result is the orange arrow. The orange arrow differs from the original red arrow by some delta v, here seen as a little green arrow. The Riemann Curvature Tensor is the object that tells us how much and in what direction little green delta v is pointed. Zero curvature means 0 delta v. We walked it counterclockwise, but if we'd walked it clockwise, the change would be in the opposite direction. A logical question might be, doesn't going back and forth along the same distance just cancel each side out? And that is a great question. That idea is called the commutation of vector addition, and in Euclidean space, that is always true. It doesn't matter the order in which you add vectors together. But in a curved space, it does. Vector addition does not commute in curved spaces. The Riemann Curvature Tensor encapsulates that non-commutativity into one hairy-looking expression. Here we can trace the progress of the metric through the curvature. We see that if we start the metric in 3 spatial dimensions, we don't have anything along the way that adds more spatial dimensions. Each of the mathematical tools just uses the metric in more and more detailed ways. We saw that the Christoffel symbols are composed of the first derivatives of the metric, and those show the gradient along a geodesic. However, the curvature tensor is composed of either derivatives of the Christoffel symbols or the product of 2 Christoffel symbols. Either way, that means the curvature tensor is composed of second derivatives of the metric. That is a change in the gradient of a path. A constant gradient or angle is not curved, but a gradient that changes is curved. But again, what's it curving into? Again, the space itself has a property that we call curvature, and that has important analogies to hills and valleys and slopes and arches, but those analogies break down when talking about spaces that are not Euclidean. The structure of the space itself has certain properties that make vectors change their orientation and magnitude as they are transported around loops. An important side quest to the Riemann Curvature Tensor is the Ricci Curvature Tensor. We see that it looks a lot like the Riemann tensor, but we're summing up on the first and third indices. To indicate this, I've changed rho and mu to A. I've also changed index nu to I and sigma to J. For those in the know, I've skipped over the Bianchi identities and the resulting antisymmetries that lightly change the order of a couple of indices. The Ricci tensor is a slightly different measure of the curvature of a space. It shows the change in the volume of a space that is bounded by short hops along nearby geodesics. If you take 2 geodesics that are initially parallel, they will bound some volume in space. Now, walk a short distance along both geodesics and measure the volume between them. The Ricci tensor tells the change in that volume. Why bother to make this thing at all? Well, remember that we eventually want to relate this back to physics, and we need to know about volumes in physics, and very often what is exactly inside that volume. I've of course skated completely around the derivation of these tensors, and I'm just handing them to you, like a croquembouche baked by a master French pâtissier. I'll have to do a full derivation video on this at some point. But if you're dying to learn, then I'll have to leave you to study proper books on relativity, such as those by Weinberg, Wald, Schutz, Hartle, or even the epic Gravitation by Misner, Thorne, and Wheeler. It's really important to point out there's a huge mathematical formalism that underpins the study of non-Euclidean geometry. Even current topics in cosmology that have arisen due to the Hubble tension that explore modifications to Einstein's general relativity, they all use the same mathematical constructs, proofs, and theorems. This is the language of space-time, no matter the physical process you're studying. Now let's see why the Ricci tensor is important. To help understand why the Ricci tensor is so important, let's calculate just one component of that tensor. We have our tools across the top. Up in the upper left-hand corner, inside the green box, are the 3 components of our metric, and in the upper right-hand corner in the purple box are all the Christoffel symbols associated with that metric. And what are we going to calculate? Below them, on the left, we see R sub RR. To get that expression, I substituted R for I and J in the Ricci tensor definition from before. And as you can see from the 4 terms, we still have to sum over A and B. I'm just going to skate quickly across these to get to the punchline. The first term is in red. Of all the possible parts, only 1 remains. The second term, in orange, keeps all its 3 terms. Note that in both red and orange terms have derivatives with respect to R. This indicates we're looking at the change in the gradient through space as we get further from the origin. In the next line, we see the term in blue. That's the 3rd term in the defining equation. Because we're summing over A and B, for each one cycling through R, theta, and phi, we could have had 9 terms, but lucky for us, 6 of these terms drop to 0. Lastly, the purple double sum also drops down to exactly 3 terms. In the next line, I collect all the terms together, and it sure looks really hairy right there. But amazingly, after doing the algebra and the differentiation, plugging the values of the Christoffel symbols into the formula and chugging along, almost everything cancels out. We're left with an extremely simple result you see at the bottom below in yellow. It just so happens that for this particular metric, which is an isotropic, homogeneous metric with a constant uniform curvature, the Ricci tensor component for this one term is very simple. It's just twice the curvature constant times the metric component that matches the tensor's indices. Now let's see what the others look like. Strikingly, there are only two other components to the Ricci tensor, and I've given them in the green box. On the left, we see the guy who started it all, Bernard Riemann, who back in 1867 gave lectures on non-Euclidean geometry. His set of lectures had an enormous impact on mathematics. The first impact was defining the concept of a manifold, which became our modern idea about space. A space, or now manifold, is dense with points, and you can lay down a ruler, or a metric, to measure distances between them. And by dense, we mean that there are no gaps between points in the manifold. You can always slice a piece of space in two and find there's still more space there. Basically, a manifold space is continuous and smoothly varies from point to point. The idea had profound impact on group theory, representation theory, and the analysis of the real numbers. It was also the spur for the creation of algebraic and differential topology. This fruitful line of work also gave rise to Einstein's general theory of relativity. To see how, we now have all the components for a tensor that describes the deviation of a volume from Euclidean space. Our metric gave rise to this extremely simple form for such a relationship. The Ricci tensor for this metric is just twice the curvature constant times the metric itself. For the near final trick, I'll define the Ricci scalar R. This is the metric summed over the Ricci tensor. We call that process contraction because it reduces the total number of indices of a tensor by 2 for each contraction. The Ricci scalar is a double contracted Ricci tensor, which itself was a contraction of the Riemann Curvature Tensor. The Ricci scalar, or curvature scalar, is just a number that measures the curvature of the manifold, read here space, that is covered by a particular metric. For the metric we developed and worked with throughout this video, the Ricci scalar is exactly 6 times the curvature constant of the metric. Finally, we have what's called the Einstein tensor, which is a construction of the Ricci tensor, the metric, and the Ricci scalar. It's been proven that this is the only divergence-free tensor that can be constructed from the metric. This is really important because something that is divergence-free in physics is a conservation law. Einstein understood the importance of this tensor to general relativity. This tensor is the left-hand side of his field equations, which relate the energy density of a space to its spacetime curvature. That's why the guy is smiling so hard. When he figured out that spacetime curvature can be thought of as conserved in a similar way to matter and energy density being conserved, he knew he'd found the link between spacetime curvature and its contents. Cosmology is, if nothing else, the study of how spacetime changes due to the evolution of its constituents. Einstein had to become very well versed in the mathematics developed 40 years prior before linking gravity to spacetime. I'll talk about the natural extension to this metric next time when I discuss the Friedmann-Robertson-Walker metric. Wow, that was a lot. I hope you enjoyed this video. If you did, please subscribe, hit that like button, and share it around on social media. I also want to invite you to become a YouTube member. You'll get videos like these earlier than everyone else, plus you'll get little bonuses. Or, if you prefer, please become a Patreon supporter. Both kinds of support go a long way to helping me get more of these videos out to you. Thanks again for watching, and we'll see you next time.